Hey kids, Charlie Busso here. Welcome to the section in chemistry called water. Water, W-A-T-A, or water, W-A-T-E-R, is everything you ever wanted to know about water, but were afraid to ask. Do me a favor, put away your cell phones, turn off everything, all right? Put some background music on, or actually listen to mine. I got some nice classical background music on. Let's just do this. I got my reference table right here. Okay, got a pencil, which is right here. I got some paper. I'm just going to do my work. I'm going to get this done quick. You're going to do the same, and we're going to make a lot of progress. Before we even get started, look at that beautiful font that says water. You can tell this is going to be a good topic, okay? Honestly, the only thing you have to know about water really wraps up into hydrogen bonding. Pretty much that's the answer to every single question, unless it's math. And if it's math, we've already done it. We're going to do the heat of fusion math, heat of vaporization math. We're going to do the delta T math. The only thing that's really new in water, we're going to look at table G. Table G is kind of a beautiful thing. It's actually a really big table. Got 10 little curvilicious lines on it and 10 different compounds that dissolve in water. It's not hard. Right? You only look at one line at a time. You put your finger on it. Yeah. What's the temperature, right? How many grams fits into 100 mLs of water? And then you just do a proportion sometimes. This is the easiest topic of the whole year. It's either review or really the answer is hydrogen bonding, or it's some simple cross multiplication and solve for X math. It's going to be a breeze. We're going to love it. Plus, it's fun to say water. Have a glass of water. All right, here we go. Look at this beautiful slide. There are 7 important properties. All the properties are caused by hydrogen bonding. Okay, there's a couple of vocabulary words. What do we know? Formula, H2O. The shape, it's bent. The atoms, there's 2 hydrogens and 1 oxygen. The kind of bonds between the atoms are called single polar covalent bonds. What's the bond between the molecules? That's called hydrogen bonding, and there it is. That's the whole point of this whole topic. And compared to other small molecules, like say methane or carbon dioxide, does water have a high or low boiling point? It has a very high boiling point because it has very, very strong intermolecular attraction called hydrogen bonding. The density, well, actually, this is a really strange thing. Very few substances have a density where the solid is less dense than the liquid. And we know that because ice cubes float on water. Right? Ice cubes float on the liquid. Now, 7 molecules, you're supposed to draw them randomly, and then we're going to draw dotted lines between them. So you can start working that out now. Now look at this top left picture. Here's a water molecule, H2O, it's bent, right? And we have what's called the dipole arrows. Now hydrogen has an electronegativity of 2.2. Oxygen has an electronegativity value of 3.4. I know that, but it is on table S for those of you that can't remember all these stupid little details. Now, because oxygen has a much higher electronegativity value than hydrogen, it's going to pull those electrons. Higher electronegativity means greater tendency to gain electrons in a bond. So if oxygen's pulling those electrons away from hydrogen more often, much more often, and that's the truth, then the oxygen side of this bond is going to be negative. The hydrogen side is going to be positive. That's why the hydrogen's got those little pluses on the end of the arrow, and the arrows point to where the electrons go. Now, water also does not have radial symmetry. You could cut it on an angle, right, through the O and have one hydrogen on either side and half an oxygen. But if you cut it in the other direction, one side will have 2 hydrogens, the other will have 2 unshared pairs of electrons. So this does not have radial pizza pie symmetry. It has bilateral or gingerbread man symmetry. That doesn't matter. It's a polar bond, polar molecule, very polar molecule, and that's why water has a lot of hydrogen bonding. Okay, there's the dipole arrows. Here it is, hydrogen bonding. It's the intermolecular attraction between polar molecules with polar bonds. Okay, and they have to have hydrogen in them. They create super duper dipoles. So this is what this looks like. These are little red and white models, little models of water molecules. They're magnetic. Which colors are which? Well, they're in a 2-to-1 ratio. So the O's, which are actually labeled there in the middle, the O's are the red, the oxygens, and the hydrogens are the white. The hydrogens are a little bit positive. That's what those funky little signs mean, the little wiggly Greek letter there with the plus or the wiggly Greek letter with the negative. The red oxygens are slightly negative, not even slightly, they're pretty negative, and the white hydrogens are slightly positive. And the hydrogen bonds are those dotted lines. They're represented by the attraction that's actually invisible, but they draw it in so you could imagine it. Now, when you get these 6 water molecules in class, if you get 6 of them, you're going to be able to magnetize them into a ring. Now, the ring's actually pretty cool. You're going to enjoy playing with these. There's a hole in the middle, and that hole is very important. Let's keep track of it. Watch the model. The white magnets bond to the red, and the red magnets bond to the white only. 2 whites would repel. 2 reds would repel, and that means 2 hydrogens would repel because they're both more positive, and 2 oxygens would repel because they're both more negative. But the opposite sides of the molecules are wildly attracted together, and that's going to make the water molecules stick together. Now, when they're stuck like this is actually a solid. The water molecules can lock into a solid with 6 water molecules. That's the standard. Occasionally, they can do 5s or 7s or 8s, but that's only under weird conditions. Normal ice has a 6-molecule hexagonal or hexagonal ring with a hole in the middle. And that hole's very important. We'll talk about it later. If you squish the molecules together, and you'll do this when you're in class, if you squish them together, you can squash them pretty tight, right? And they take up less space than when they're in a 6-molecule ring. That's because the density of pure water is 1 gram per centimeter cubed. We could say it a different way. You could also say 1 gram per ml. 1 gram of water is 1 ml of water. We kind of make that the standard. But when you put it in a ring, you still have the same mass, but it takes up more space because they're further apart. There's a hole in the middle, and that makes the ice slightly less dense. I mean, you're talking about a couple of hundredths of a gram per ml, but it's enough to make ice float on water. The density of ice must be less or lower than water because ice floats on water. The hole in the ring, the hole in the 6-molecule ring, that little hole, you can put your finger in because it's a plastic model, but it's very small, but it's real, makes a slightly greater volume. Look at that picture of an iceberg. Icebergs are freaking gigantic, huge, and they weigh a lot, but they float. You know why they float? Because no matter how big it is, the ocean is bigger, and the ice is less dense than water. Ice cubes float in a glass in your kitchen, right? If you threw a big 25-pound block of ice, you can buy that in some of the ice shops around town. You throw it in your swimming pool. It's actually a fun toy. Throw a big giant ice cube and try to push the ice cube to the other side of the pool, and it floats, right? It floats because it's less dense. What temperature does liquid water freeze? This is standard temperature, right? You know this already. Table A, right? 273 Kelvin or 0 degrees. Now to melt 1 gram of ice, this is thermochem from way back, right? To melt a gram of ice into a gram of water, we must add the heat of fusion. Now, if we wanted to do the reverse, if we wanted to freeze a gram of water into ice, we'd have to remove the heat of fusion. And for water, it's a constant in table B, 334 joules per gram. It's review. It's hydrogen bonding, or it's review. Now look at that beautiful picture. Like that hand? There's an ice cube in that hand. That's not my hand. It looks like my hand. All hands kind of look alike. Put an ice cube in your hand. Your hand gets cold, right? You knew that. You don't even have to do that, right? How come your hand gets cold? What's going on? How come your hand gets cold? Does the cold go into your hand or what? What? That's what happens. The heat energy is transferred out of your hand. The heat is going into the ice cube. That's why the ice cube melts. Your hand gets cold because there's less heat in it. The cold does not go in. Cold is nothing. The heat energy transfers. In between your hand and the ice, your hand has way more kinetic energy, way more temperature. And when you put the ice cube in it, in order to balance that, the heat leaves your hand. It actually melts the ice cube, but it leaves your hand, making your hand more cold. Your hand doesn't get cold. It gets less hot. That's what happens. It gets the reverse of hot. The heat leaves. Heat can move. Cold is nothing. Now, The energy takes to melt ice. Oh, I don't know what happened there. The energy takes to melt ice is called the heat of fusion. For water, it's 334 joules per gram. How many water molecules does it take to form a normal crystal of ice? 6. How many points or sides do all snowflakes have? 6. Look at these beautiful snowflakes. Every single snowflake has 6 sides or 6 points or 6 somethings like that. I don't know what you call the one on the bottom left. That's really kind of funky. The rule of thumb is that every snowflake is different. I don't know if that's true. There's a lot of snowflakes. I just can't imagine that they're all different. But there's many, many kinds of snowflakes. And the similarity for every one of them is that they have 6 points or 6 stars. Why do you think? Because water molecules freeze into ice with 6 water molecules. And then it grows and grows and grows in 6s. And there you have it, okay? They grow in 6s and they're kind of cool. Snowflakes are cool. They make me hungry. They look like cookies. Now, we're done with 6. We're going to do 7 now. The 7 most important properties of water and what causes them. Ready? Number 20, water has a very high boiling point. The reason water has a high boiling point is hydrogen bonding. It's always hydrogen bonding. Now, what does this mean? When water molecules are in a pot, and you put them on the stove, and you put the stove on, and the heat's coming in, the water molecules start moving faster and faster and faster. Water doesn't want to boil till it gets really, really hot, 373 Kelvin, which is not terribly hot like compared to the sun, but compared to the boiling point of all small molecules, it's incredibly hot, right? Carbon dioxide, you've never even seen it as a liquid or a solid. Why? Because it boils at like, I don't know, minus 45 Kelvin. I'm sorry, no. Minus 45 centigrade, nothing's minus Kelvin, right? Minus 45 centigrade, water boils at 100 centigrade. Hydrogen bonding holds it together so tight, you gotta really shake them apart with heat before they blow apart. Okay, water has a low vapor pressure. Why? Hydrogen bonding. Now, what does that mean, low vapor pressure? It means it doesn't evaporate very well. Remember I told you about my daughter painting her nails and then taking that nail polish remover to clean that polish off to do it again? I hate that smell. If you had a glass of water and a glass of nail polish remover, you put it on a table somewhere in your garage or your house or your back porch or something. You fill them both up to 100 mLs, exactly the same amount. Water has a very, very low vapor pressure. That means if you evaporate it in a closed system, there'd be very little extra pressure. What that really means is it doesn't evaporate so hot. You watch them, and in 24 hours, the nail polish remover is gone. It evaporates into the air. The water is still there. Water lasts a long time. You know why? Because it is hydrogen bonding, and the water doesn't want to go into the air. It wants to stay stuck together, right? When you wash your hands and you go outside and it's cold out, your hands get cold, right? Your hands get cold because they're wet. If you use that hand sanitizer and you don't even go outside, you just go like this with hand sanitizer inside, you know what? Your hands get really cold. You know why? Because all the molecules of the alcohol in the hand sanitizer, they evaporate really quick. They have much less hydrogen bonding. And when it evaporates, it takes the heat out of your hand and makes your hands really cold. Okay? Hydrogen bonding. It's really cool stuff. Okay, look at this ugly bug. Listen, let me tell you a quick side. I know you don't like my stories anymore. Sometimes kids like my stories and sometimes they don't, but here comes one. I grew up in New York City. I learned how to swim in a pool. They used to have to walk to at the park. Nobody I knew had a pool. Nobody had any money. Nobody could have a pool. But at the park, they put so much chlorine in that pool because, you know, the filthy kids in the neighborhood probably never took a bath like me. They had to swim there, had to keep the water clean. Nothing could ever live in that pool. And there was no like open water that you can go to except the beach. And the beach at Rockaway Beach, the water was so polluted and brown, nothing lived in there either. You never had to worry about getting eaten by a shark. The sharks would be dead before they found you. Look at this filthy bug. Oh my God, this is like one of the grossest things in the world for me. When I first came upstate, I went to college in Cortland, and, you know, I'd go to Ithaca, go to like Buttermilk Falls or something to go swimming in the water. And I saw these bugs and it was like, oh, ski bots. Oh my God, what is that? I can't believe it. These disgusting insects can walk on water. How the heck can they walk on water? Hydrogen bonding. Listen, water has what's called surface tension. and it's due to hydrogen bonding. And what that means is the water not only sticks together, but at the surface, it's really amazing because the surface is a very interesting place for a glass of water or a pond or something like that, because the water sticks together in every direction because the hydrogen bonding is going in every direction. But at the surface, it sticks together side to side very, very tightly and down. But there is nothing to attach to up. Up is the air, up is the not water. So at the surface, the water really sticks together side to side. It makes like a skin, almost like a drum. When you hit the top of a drum, it gives a little. Water gives a little. I mean, you can't walk on water, right? You're too big, really. The surface tension's not that strong. You aren't too big, but the water can't hold you up. The hydrogen bonding's not that strong. It will let a person walk on you. But a little bug, horrible. Look at these disgusting bugs, all right? They can walk on water. You know why? Surface tension. Also, you want to play a game? Go in your bedroom and get some talcum powder, right? Get a glass of water, shake some talcum powder on there. You look up the density of talcum powder, it's greater than water, but it floats on top. You know why? Because the density of the bug or the talcum powder is a little bit higher than the density of water, but that surface tension gives the water a little extra oomph to hold it up. This is disgusting. I hate this picture. This is a good picture. This, you know what this is? Love. And love is the best. All right. Solid ice. Look at that. You know, remember this movie? Titanic. And what did that boat do? It crashed into an iceberg. And what does an iceberg got that you ain't got? Well, you got some. Hydrogen bonding. Oop, I went too fast. Let's just talk. I guess I don't have the answers here. Solid ice can float on liquid water due to, you got it, hydrogen bonding, right? When that six-sided ring forms, there's a little hole in the middle. That makes the ice less dense. Doesn't matter how big it is, all of it's less dense. So it floats, right? And during this movie, Titanic, they're like, look at us, we're in love. I'm rich, you're poor, it don't matter, right? And a little bit later, in the dark, they crash into a big freaking iceberg and almost everybody dies. It was a terrible, terrible, terrible event. It's a good movie. You should watch that movie. How come that movie's good? Hydrogen bonding. Leonardo DiCaprio and Kate Winslet also very good. She's a great actress. And I hate to admit it, he's pretty good too. All right. This is another great love story. You want to watch a good love story? Disney does some good ones too, right? Look at that beautiful face. You know what happens in this scene? They're both sucking that spaghetti. And as it turns out, it's the same long strand of spaghetti, which is like a 1 in a million shot, right? And then they do a quick little kiss and woo, the kids go crazy. Love stories are wonderful, okay? Hydrogen bonding. Next up, look at this cute little kid. I wish I knew her because she's so cute, but I right-clicked on her on Google. I found a little cold kid by a pool. All right, if you have a pool, I have a pool now, right? I'm not as poor as I used to be because I'm a teacher. I got a great job, and you want to have a great job, you should be a teacher too. I was having a pool party for my daughter, and my pool heater died. I'm like, oh my gosh, what am I going to do? The pool is so cold. I had to buy a brand new heater. The only heater the guy had was too big for my pool. I said, I don't care, got to have it, got to bring it over right now. He brings it over, it won't fit into the little pool house. I had to cut a big hole in the back of the pool house to get it in, but it worked like heck. Now listen, if you have a pool and you don't have a heater, you're a good person, but in the summer, your pool, no matter how hot it is outside, is a little briscola, a little chilly. You jump in there and it's like, whoa, you're refreshed, right? Like this little girl, right? The water's cold. This is the public pool. There's no heater. They don't like to spend money on, they don't spend tax dollars on poor little children. They go in a cold pool. They don't care. It's terrible, right? Water has what's called a very high specific heat capacity constant. That means it takes a lot of energy to warm it up. And the sun is just not strong enough to warm up a big pool, right? You want to have a warm pool for your kid's pool party, you got to get a heater. If you have a heater, the combustion works really well. Right? Combustion is when a hydrocarbon and oxygen combine to carbon dioxide and water really fast, release a lot of energy, makes the pool water warmer. Why does water have a very high specific heat capacity constant? How come it's hard to warm up the water? Because to warm it up, you got to make those molecules move faster. They don't want to move fast. They're sticky. They're all hydrogen bonded together. You got to overcome all that hydrogen bonding to make them move faster. The faster they move, the hotter it feels. It takes 4.18 joules for every gram of water to change temperature by 1 Kelvin or 1 degree centigrade, because it's the same amount of change. Look at that cute little kid, she's freezing. Now, water has the ability to create solutions. right? When you shake some sugar into water, it disappears. When you shake some salt into water, it disappears. When you mix a lot of things together in water, they disappear. This is called, ready? It's called salvation, not salvation. Salvation happens in churches and mosques and synagogues and places like that. Nobody's getting saved here. They're getting salvated. Salvation is when the water, which has positive and negative sides, right? The hydrogens are positive and the oxygens are negative. They get at these polar molecules or these ions and they sort of juggle them. The water arranges itself by charge around the ions or around the polar molecules, right? Why does stuff dissolve in water? Hydrogen bonding, right? And this can be stated more casually. This is a great three-word sentence. Like dissolves like. Water is polar. It will dissolve other polar substances or ionic ones because ionic ones turn into ions, right? There's a few exceptions. Some ionic things will not bond in or not dissolve in water. They're too tightly bonded. But generally, the rule is like dissolves like. Polar water dissolves polar molecules and most ionic compounds. Water has the ability to form what's called a hydrated ionic compound. Now, what the heck does that mean? You know what this means, actually. And why does it? Because it's hydrogen bonding. The examples we have here are CuSO4.5H2O. That's called copper Roman numeral 2 sulfate pentahydrate. Now, earlier in the year, I think we saw a video about this. Usually, you would do this in class, and then you do the other lab with the magnesium sulfate heptahydrate. That dot in the middle of the formula is, at the beginning of the year, it's called loosely bonded. Now we know it's hydrogen bonded. Water can attract itself onto certain ionic compounds. Now with CuSO4, 5 water molecules fit, but with the magnesium sulfate, seven water molecules. That stuff is actually called Epsom salt, right? They indicate hydrogen bonds. And water can do that onto a lot of ionic compounds. Now this is the last slide. We have to go through these quickly. These 11 vocabulary words, they got to go in your head. You don't want to memorize these. You're never going to amount to anything, right? One day in the future, your child, if you're old enough, don't have a child till you're older, but your child will say, hey, mom, hey, dad, what does immiscible mean? Or what does insoluble mean? You got to know these words. Ready? Salvation. Salvation. That means the process of dissolving in a liquid. Okay, in this case, we're talking about water, though. Solute is the stuff that gets dissolved. Solvent, in this case, would be the water. That's the stuff that gets the solute dissolved into. Now, immiscible and miscible are hard words. Immiscible means when two liquids will not mix because there's a difference in polarity. Oil and water. Water's polar, oil is nonpolar. They will not mix, right? Miscible is when two liquids do mix, right? If you mix some vodka and some water, which you should not do, but they're both polar, they will dissolve into each other. Aqueous is the vocabulary word that means dissolved in water and not dissolved in other things. Things that dissolve in gasoline are not aqueous. And there are some things that dissolve in gasoline. Soluble means you can dissolve, and insoluble means you can't dissolve, right? Some compounds, like sodium chloride, are soluble in water, and some compounds, like silver chloride, are insoluble in water. You put them in, and they don't really dissolve at all. Now, saturated. Saturated means a solution, in this case maybe an aqueous solution, is holding an absolute maximum amount of stuff in it. Unsaturated means there's less stuff in it. There's room to add more solute. And let me tell you what this means. I always joke about my chocolate milk. If you came to my house, I always tell kids, you should come to my house. I have 3 cute little pot-bellied pigs, and I named them Mo, Curly, and Larry because those are the 3 stooges, right? And I say, come, you guys are all invited to my house. We'll go in my kitchen, make you all chocolate milk, right? And we're gonna look at my 3 little pigs. And you go outside and you can pet them because they're really cute. And they make little sounds. Now, if I was gonna make you chocolate milk, I know how to make chocolate milk, right? You get a glass of milk, squirt the hell out of the chocolate stuff, stir it up, and my chocolate milk is perfect, dark chocolate, rich, beautiful. But if Janet's there, like if I'm out in the yard with some kids and some of you kids show up a few minutes late and Janet, my wife, makes you some chocolate milk, she's worried you drink too much sugar, eat too much sugar. So she's gonna give you a glass of milk and a quick little squirt of chocolate, stir it up, and your chocolate milk's gonna look like gray water. You're not gonna want it. It's gonna Room for plenty more chocolate sauce. So saturated means full. Unsaturated means Janet made your chocolate milk. There's plenty of room for more solute. Now, supersaturated is a really cool word. I got to talk about it. Some things like sugar do dissolve in water. If you have 100 mLs of water, you can fit a certain amount of sugar in it. Now, what's cool is if you heat the water up, more sugar fits in it. Now, for most substances, if you have a hot solution, you can put a lot of salt in it, say. And when it cools down, because it's colder and the cold water can't hold as much of the salt because the hot water can hold more, the water juggles faster. As it cools down, salt falls out of solution because the water can't hold it anymore. But a few things, including sugar, if you start with a really hot solution and you let it cool very, very calmly, right? You put it in a corner, nobody's shaking it, nobody's bumping into it. The sugar doesn't realize that it's cooling down, neither does the water. The sugar fools it, and the solution actually has now more sugar in it than you could put in if the water were cold. If you start hot and you add a lot of sugar, it'll all dissolve. If you cool it off, all that extra sugar stays in it. If you started with the cold water, you could never get all that sugar in. So if a solution happens to somehow have more solute than is normally possible, right? It's because you started hot and you cooled the solution. You didn't start cold and try to mix it all in. You can be what's called supersaturated. And that's how you make rock candy. And we'll try to do that. I'll try to set that up and we can see if it works over a couple of days because it takes a few days. All right. That was class 1. Water, H2O, hydrogen bonding. Gotta love it. This is going to be an easy topic. All right. Bye-bye. Over and out. Peace, love, and